I want to introduce Dan Marsh, who's going to be talking today about this energetic particle precipitation effect on the atmosphere. So Dan got his PhD from the University of Michigan, working in the Space Physics Research Lab. And he came to NCAR in 1999 as an ASP postdoc, the way many of us first came here. And he then became a scientist in atmospheric chemistry division, which we used to be. And he's been here ever since. He works on the WACM project, so he's the ACD lead of the WACM project, and he's also the head of the global chemical modeling group in ACD. And
all right, thanks.
There you go. Let me turn this off.
Okay, yeah, so I'm going to talk about this, the response to the middle atmosphere of energetic particle precipitation. And I'd like to start out with some motivation. So I think one of the grand challenges in atmospheric research right now is to achieve seamless prediction across all timescales. And if you heard Julia Sliglow's talk earlier or recently, she said that the sweet spot is 1 month to seasonal to decadal timescales because that is where most decision makers work, and that is where people will be making the big investments. So that's the big challenge, is to sort of come up with improvements in our predictions over sort of those timescales. And so I'm going to suggest perhaps a path forward to, in achieving a better prediction on these sort of up to decadal or 20 to 50 year timescales may be a better representation of the forcing across those timescales, as well as a better representation of the response. So this, is another avenue in addition to, say, going with higher resolution or better initialization. But one of the motivations for that about and why I think the stratosphere matters on those timescales is, and this is just one example of the importance of the stratosphere in tropospheric climate. The top figure shows the southern hemisphere temperature trend, and this is by month and height from 0 to about 50 kilometers. On the left-hand side is a figure showing a left panel here of the temperature response in WACM from the trend from 79 to 2003. And you can see, I think this is a trend per decade in temperature. And the right-hand side is CCSM4, which had a relatively weak ozone hole. You see there's a much stronger response in the left panel. And that change was manifest in changes in surface climate. So the bottom panel shows zonal mean zonal wind trends. On the right panel, the precipitation in DJF. And this is now a function of latitude here. And the two lines I want you to look at are the solid line and the dashed line here. So along with this stronger response in the stratosphere, you see a stronger response in the troposphere, the surface. And this comes along mostly because there was an enhancement or a change in the sudden annular mode associated with this change in ozone. So that's just one example in the southern hemisphere. There are, so what I want to suggest now is that, or ask, does variability in solar forcing play a role in this sort of decadal variability? So this is a figure adapted from Leslie Gray's review of the solar influence on the atmosphere. And the left-hand panel is sort of focusing on the irradiance side of the puzzle. So we have the total solar radiance varies by about 1 watt per meter squared over the solar cycle. And that has a direct component, what we call this, which will go straight to the surface and has possible effects on heating the surface and feedbacks through cloud parameters. This is kind of work that Jerry Meal's done. And then you've got the pathway through the stratosphere. So UV, which varies on more than the visible or the total solar radiance, the shorter wavelengths vary quite a bit more. So that will have two effects. It will heat the stratosphere, and it will also create more ozone. More UV photolyzes more O2, and you'll produce more ozone. And then there's a whole series of possible mechanisms. The most popular one is that by changing the temperatures in this region of the atmosphere, you change the meridional gradient of temperature, and that will have a response in the wind field. That response, that change in the wind field, will then change the propagation of planetary waves up into the stratosphere. And you may have slightly, they will be refracted maybe preferentially to the equator or to the pole, depending on this change. And then it might affect such things as the frequency of stratospheric warmings, and those things will propagate down. So in the northern hemisphere, there's a mechanism by which this might affect the surface climate through affecting dynamics. Another process by which you might change ozone, though, is through energetic particles. And they will produce NOx, which I'll just go into in the next slide. And NOx will, within catalytic cycles, destroy ozone. So NOx maybe is an important part of this problem. And I'm going to just motivate what I'm doing now by looking at our current state of how we do NOx in Wacom. So this is a slide that was sent to me by Erkki Karola at the Finnish Met Office, or Institute. And the solid lines represent the NOx as observed by the GOMOS satellite. And the dashed lines represent Wacom. So this is a polar cap average over a number of years. So you can see we're missing something here. We're missing NOx in the high latitudes. Okay, so that's sort of motivated my talk, hopefully. So here's an outline. I'm going to go into what I mean by odd nitrogen and energetic particle precipitation. I will then look at, show you more examples of where how poorly the current version of Wacom handles this NOx at the high latitudes in winter. And give you two solutions, which I think the combination of both will go a long way to solving this NOx deficit. And then from there, I'll show you the ozone response, and it's not negligible, and then how that may have implications for decadal variability. Okay. So this is a figure showing NOY. So some definitions. NOx is the sum of NO and NO2. EPP NOx would be the NOx that is made from energetic particle precipitation. And then NOY is a bigger family, which represents NOx plus nitric acid, N2O5, chlorine nitrate, and other species. And what happens is that some of the NOx will come down and become transformed into these other species. And so you need to keep track of all of NOY when you're trying to look at the budget for NOY and its impact on ozone. So the bulk of NOY in the stratosphere, so this is 1 hectopascal, 50 kilometers, and this is roughly the tropopause here. So the bulk of NOY comes from surface processes. So such things as nitrogen-fixing bacteria, application of nitrogen fertilizers, industrial processes, and burning of fossil fuels. So that's N2O. N2O is produced down here, below in the troposphere. It will come up. Typically, it will be transported through the tropopause in the tropics. And then N2O will react with O singlet D to produce two NO molecules. And why O singlet D? Well, O singlet D is a product of ozone photolysis. So the UV is absorbed here, makes O singlet D reacts, and so you get your main NOx production here. So this is where the bulk of the NO. There's also this up here, and this is this EPP NOx. The NOx is made higher in the atmosphere, and you can see it clearly in this plot from this the ACE instrument in June, July, August. Okay, so here's an illustration of the processes of energetic particles as they come into the atmosphere. So this is, there's a fair number of things going on here. The green lines, these sort of thin lines, represent the magnetic field. These sort of kind of light orange colors represent the Van Allen belts, the belts of ionized plasma that were, I think, first discovered maybe 60 years ago by Van Allen. And then the little squiggles, those are electrons and protons, the energetic particles, that move up and down the field lines. And they are kind of constrained in what we call a magnetic bottle. They go back and forth, following these gyroscopic motions. As they come closer to the turnaround point, where they are then reflected back, they have a chance that they're going to interact with the atmosphere. And maybe they get dislodged, or maybe there's a perturbation in the magnetic field. They'll start to penetrate into the atmosphere. Okay. So depending on their energy, they precipitate to different depths. So this is our solar protons, and one side of the equation. We've done a lot of work on studying solar protons. We have many papers there. And these happen infrequently, but then when they do happen, it's a big effect. Energetic electrons, well, we've always had an aurora in WACM from the very beginning. And that makes, those are representative of a few keV. And they will produce Nox in the thermosphere. So the big missing part of the puzzle is that we've never really put in medium energy electrons in a long climate run. So that's what I've been doing. And depending on their energy, they will come down to, down to about 50 kilometers. So as they come down into the atmosphere, probably this is just for the chemists in the room, but up in the E region, then the product, when you ionize something, when a particle hits, it will cause a cascade of secondary electrons. It's got a lot of energy. That will ionize the major species, and through some chemical reactions, you end up making some Nox. The chemistry gets gets quite a bit more complicated in the D region, lower in the atmosphere, and we take the approximation, which is a very good one, that we're going to make about 0.7 N2Ds and about 0.55 ground state nitrogens for every 35 EV. Remember, we were talking about an MEV here, so there's making lots of Nox. And then that N2D is likely to make nitric oxide. Okay. So when it comes down, this is now a figure showing the circulation in the upper atmosphere. And so you've got this Nox being made in the auroral region that we've always had in the model. And at high latitudes, this preferentially comes down in the poles. You've got this medium energy electron production. If it's made outside of that region, so this is for southern hemisphere winter now, where the circulation is downward over the winter pole, then it's going to be lost because at least above 50 kilometers UV will photolize NO, and it'll be lost. So it needs to be produced in sort of polar night for it to be effective. Once it gets below 50 kilometers, there's enough attenuation of the UV that it has a much longer lifetime. So we've decided, but if you look here, you see these lines, they actually kind of go upwards here, which will be a problem. But what we think the important process here is that there is actually molecular diffusion and eddy diffusion transporting Nox downwards out of the thermosphere, and then it can get entrained in this circulation and brought down into the stratosphere. So this is, we're going to look at these effects now in the WACM model, for those that aren't too familiar with that model. It's part of the CESM, Community Earth System model. It has a lid at about 140 kilometers. The simulation I'm going to show are around nominally 2-degree resolution, and it all has fully interactive chemistry. In these simulations, and this is an option, I'm going to nudge the model to reanalysis. So I'm using it essentially below the stratosphere, or below 60 kilometers, essentially like a chemical transport model. The winds are overridden and identical across all the runs. That way we can separate out the chemical response from the dynamical response, because otherwise you'd have to run many ensembles to pull out this sort of signal from the EPP. Okay, and all models they're time dependent. They're going to have a varying solar cycle in them, varying aurora that is driven off a KP geomagnetic index, and solar protons are in all these runs. So this is an additional process they're adding. And for those that might wonder how we get eddy diffusion in the model, it's tied to the gravity wave parameterization, which is triggered in the troposphere from convection and fronts. Okay. So this is the auroral parameterization that's been in the model for a while. This is a picture of Nox produced for a particular geomagnetic activity and part of the solar cycle on the right-hand side. And you get these very large concentrations, 10 to the 7 per cubic centimeter of NO in the thermosphere. And then the left-hand side is this nitric oxide empirical model I developed based on the snowy observations. And the comparison here is that, I hope you agree that it's reasonable agreement between these two. So at least the source region for auroras is, I think, pretty well done in Wacom for the auroral Nox. Okay. Now let's look down lower in the atmosphere. So this is a paper we just submitted with Prandtl, comparing 2004 January, February, and the solid line represents, this is now 40 to 56 degrees north, so kind of close to the polar night, or high latitudes here. And you can see that the solid line represents a halo. This is a upper atmosphere research satellite instrument. And the dashed line is the simulation for Wacom. So you can see here that maybe we're only getting 10 to 15% of the NOx here. So we certainly have something missing here in the 60 to 80 kilometer range. This is exactly where these medium energy electrons are coming down. So I showed this figure before. This is from GOMOS. So this is, again, 70 to 90 degrees because it's stellar occultation from Sirius. So it's a northern hemisphere observations. And the other point I wanted to make about this is that you can see here the discrepancy is much worse in 2002 to 2006 than it is from 2007 to 2011. So you can see that this maybe has a solar cycle dependence. We had a very, very deep protracted solar minimum. Here we had, closer to solar maximum. So it may be that this deficit is related to the solar cycle. Comparisons out at mid-latitudes, well, we're actually doing pretty good. So again, pointing to this error, something to do with the process that occurs near the poles. Okay, so back to this figure from ACE. And the peak is around 20 ppb here, and this is this amount here. So now I'm focusing down 65 to 20 kilometers. So I'm going down into the stratosphere now. And here's what we get for Wacom. So you can see there's a hint here, a little bit, but we're really missing something out here. Northern hemisphere, you get this nice strong NOx coming down here. And when you compare that to Wacom, there's nothing there. So how am I going to solve this problem? So two solutions. One is to increase this diffusive flux down from the thermosphere. So in order to do that, we need to increase the KZZ, the vertical eddy diffusion coefficient. And I'm going to say that I'm going to hopefully give you a reasonable argument that doubling of that coefficient is not an unreasonable thing to do. And then we're going to implement these outer belt medium energy electrons, and they're based on pose data, which I'll describe next. Okay, so KZZ, this eddy diffusion coefficient, this is a paper by Rolando Garcia using the Wacom model. And here we looked at CO2 and CO. And here I'm just going to show you CO2. And so this, again, ACE data. Here, there's two sets of data. Those are the little symbols. And the solid lines are for two different latitudes. And what you can see is that, and then for two different model configurations. One is this base standard model, which has a Prandtl number of 4, and one with a Prandtl number of 2, which effectively doubles the vertical KZZ. And you could argue that really between the two, there's not much to it. So I think maybe a doubling is reasonable. And I think, in fact, this will probably be the default, is we're going to go with a Prandtl number of 2 from now on, based on this and some other work we've been doing. We're not free to turn this knob. So this is not just sort of something I can go in and crank up and get as much NOx as I want. Because if I do that, I'm going to destroy the ozone distribution, the water vapor distribution, and a few other things. So this is, again, a reasonable thing. For instance, if you had a very, very strong diffusion, then this profile would continue to go up in the model. Okay. Okay, so, and now these outer belt electrons, so they come in sort of on essentially zonally symmetric in geomagnetic latitude, which means that because of the offset of the pole, they come in more symmetrically in the northern hemisphere than they do in the southern hemisphere. And we're going to put these based on this MEPED instrument from the Polar Orbiter. It's a NOAA instrument. And the fluxes are zonally average, so we're just putting them in evenly on geomagnetic latitude. And the resolution, so these are two different, they go between geomagnetic L shell 3 to 7. I've drawn them here so that you get an idea about where they're coming down in the atmosphere. And we're going to put them in at 3-hourly time resolution. So this is just 1 year of MEPED data, 365 days along the bottom here. And what we've done is there was some issue with contamination for the solar protons. So we just, playing it conservative here, just removed the data during this. There was a solar proton event in here. This is the Halloween storm. So we just removed it. And these are the integral fluxes, so greater than 30 keV, 100 keV, and 300 keV. So these are the ones that are going to get down into the lower mesosphere. And so that's the measurement out in the atmosphere, or sort of out in space. Here's what that produces as far as ion pair production rate. So there's the ionization frequency in the atmosphere. So I took a slice here at 78 south. And there is, in the file, there's no ionization below 50 kilometers. So all the effects you see below this atmosphere have to be transported down from there. And so the two things I want you to see is that you can see that it's producing, the medium energy electrons are producing NOx in the sort of 80 kilometer range, peaking here, but down to 60, and that there's this solar cycle variation in this. So much more ionization here in the 2003, 2004 than in the depth of that solar minimum here. So just quickly, I guess I'm going to show you some results from a series of numerical simulations. Standard one with no MEE, one where I just enhanced the KZZ, and one where I enhanced MEE, and then the combination of both. So this is the response now of NOx in the mesosphere from a doubling of the KZZ only. So you can see now, and this is for May in 2003, you can see up to a factors of 3 increase around 80 kilometers. We're looking maybe factors of 5 total. So, and the same plot from just the MEE now. And here we're seeing up to maybe almost factors of 4 here. So producing NOx now where we need it, down here in the high latitude mesosphere. There's actually not many observations to compare to. I'm trying to collect more and more data to compare to these things, but just one comparison in the mesosphere. And so this is based on MEPAS observations at 77 degrees latitude, north and south, at 0.1 hectopascal, which is around 65 kilometers. So maybe I just want you to focus on this one part here. The dotted line here is the base model. You can see that this dotted red line is where I added in the medium energy electrons, and then the solid line is where we increase the KZZ, and the sum of them is up here. So even in some years where maybe still have a deficit, some years is getting into better agreement, but certainly much better than the base model. So now let's go back and look at that figure based on ACE, the NOY, and now we're getting this amount, this NOx produced up here at high latitudes. And if you can't remember that figure I showed you a number of slides ago, then here's the combination of the figures. So right-hand side shows Wacom NOY from the base model, and then this new MEE source compared to the observations here. So you think you agree that the agreement is now much better between the model and the observations. Scale goes to 20 ppb for these 3 panels, and in this panel I've shown the difference of these and I've doubled the scale. You can see that down here, even now in the upper stratosphere, we're getting 2 to 5 ppb extra of NOY. So not a small, inconsequential amount in the NOY budget. In the northern hemisphere, again, this is now, we're seeing that nice strong northern hemisphere signal, 2004 to 2009. and again, the combination plot here. So really, I think now you can see that we're getting something like 10 ppb or more in the lower mesosphere, and still, maybe 3 or 4 ppb at the high latitudes during winter. So this is, DJF average. And again, I think you agree, the agreement now is much better than before. So next I would like to talk about what happens to ozone because of this change in the NOx. So this is a figure showing, on the right-hand side, the odd oxygen. So what I mean odd oxygen is the sum of atomic oxygen and ozone. Relative contribution. So Doug Kinnison made this figure. It shows the importance of these different catalytic cycles. One of them being the Nox Catalytic Cycle. What I mean by catalytic cycle is this is an illustrative example. So you'll have NO plus ozone will make NO2, and an O2 molecule. That NO2 will then react with an atomic oxygen. So both sum of these is the odd oxygen family. Make another O. The net of this, and you get your NO back. So the net of this is that two odd oxygens make 2 O2 molecules. So it's an important process. And in this region of the atmosphere, it's actually the dominant process. So certainly above 25 kilometers in this time of year. The Clocks and Brock's cycles, the ones that are responsible for the loss in the ozone hole, more important lower down. So now here is a figure showing the ozone difference in August. So this is now after winter. So you made this extra NOY in the atmosphere. But for that catalytic cycle to process, you need atomic oxygen, which means you need sunlight, because otherwise that O will just recombine, and if it doesn't get photolyzed, it's just going to stay in the ozone state. So you need atomic oxygen around. So this effect happens in the springtime. You've got this now decrease of ozone up to 6%, all the way down, seeing decreases down all the way to 35 kilometers, so covering essentially the whole polar upper stratosphere. You can see this propagate downwards. So as that wind continues to come down, now we're getting up to 7% changes in ozone here. You might notice that we lost that signal up in the upper atmosphere, where before we had loss in ozone up here. Now we don't, and if you recall, above 50 kilometers, that ozone didn't escape being lost from photolysis. So only when that NOI can get down into the safety of the stratosphere can it start to destroy ozone. So that's why we see this difference between the months. In this northern hemisphere now, I'm looking at February, the signal isn't quite as strong. It's about 3.5%. And again, this is related to losses in the mesosphere. The northern hemisphere winter will have stratospheric warmings, and those will end up just pushing the air out of the polar regions and into a region where it can be photolyzed in the mesosphere. So unlike the southern hemisphere, it has a very, very well-defined, very cold vortex, and so that it's free to bring the NOI down. Here you're going to see more losses as it comes down from the thermosphere and mesosphere into the stratosphere. So you see a weaker signal in the northern hemisphere, but still it's about 3% here in the northern hemisphere in spring. So here's just showing you the progression now, and you can see that as it oscillates between the hemispheres and winters, how it propagates downwards between each of the hemispheres. Okay, so you can say, well, okay, 6%, 7%, how, is that a big deal? Well, this is a figure from Leslie Gray's summary showing the response of UV of the fit of sort of multiple linear regression fits to SAGE observations where they try to pull out the solar cycle. And the changes from max to min from 1985 to 2003 are on the order of 4% in ozone. So the signal is always larger than the signal seen when people are trying to look at drivers of, variability from UV. There's also, of course, the UV variation in the heating rate. But still, this is, the variations in ozone are larger, and they will have changes on the shortwave heating rates. Remember now that I showed that at solar max, you had a decrease in ozone. So this is actually additive. These two processes will work together to give you the same sign. If we think of that process by which you change the meridional gradient in temperature, and that affected the winds and the planetary propagation, a decrease in ozone at solar max from the EPP. And now you have a positive effect here, means that that gradient and that forcing will be stronger. So these are additive. You're going to get, it's not going to cancel the solar effect, it's going to amplify it. Okay. And again, just to point out, of course, that EPP varies with the solar cycle. Although it doesn't exactly vary with the solar cycle. It tends to peak on the declining phase of the solar cycle. You always get these more solar storms as you come out of solar maximum. And that sort of is, I thought that was interesting, and this is now a little bit speculative, I agree, but this is this paper by Leslie Gray, 2013. They did multiple linear regression of 140 years of sea level pressure data. And what they see is that at lag 0, they see a response in the Aleutian high in this SLP. Okay. But when they look, the strongest response they see in the Atlantic and in Northern Europe is actually lag 4. So could it be that instead of this being a lag response, which they argue has something to do with the ocean coupling, but they cannot produce this in the current models? Or is this perhaps maybe a signal that we're getting these events occurring on the declining phase of the solar cycle? Okay. So, so what's the next steps? So I did all this in a model with constrained dynamics. So I can't really get at the dynamical response and the response down to the ocean. So the next steps would clearly be to put these processes into a free-running model with and without, and to try and estimate this in some sort of ensemble approach. There still seems to be some uncertainty on this forcing. Maybe we could even do with more Nox compared to the observations. I'm going to continue to do some validation. But we're also starting to look into maybe getting data from the NASA Van Allen probes and this new NSF CubeSat, which can not give us integral fluxes, which you then have to fit to a spectrum, make some assumptions, but the differential electron fluxes. It will actually measure the energy spectrum. So hopefully we've put in a guest investigator proposal with the University of New Hampshire to see about putting these into WACCM. And then I think for modeling purposes going forward, what's the effect of this EPP on a sort of maybe 50-year time scale? So this is a figure I got from Scott McIntosh that bandogram, is that what we call this? So this is, I guess, magnetic polarity, and you can see that it has this, the interaction between the north and southern hemisphere produces variability in the TSI. So this is possibly a way in which we could make predictions over the next 50 years about the variability in the solar cycle. What would happen then if we went into a grand solar minimum and we switched off this EPP loss? Well, we also know over that same period we're going to get rid of the CFCs are going to, their effects is going to diminish, and we're going to have the ozone hole will recover, right? On top of that, you're going to have cooler temperatures because of the CO2 cooling of the stratosphere. And what we get is what we call a super recovery of ozone. A third thing now, all going in the same direction, is we're going to be producing less NOx, making higher ozone in the poles. So now we've got three things all working in the same direction, changing ozone in the stratosphere. A distribution of ozone that's not in any model, in any projection. This is our or RCP 8.5, but all of these would add up. What would be the effect, say, in 50 years if we went into grand solar minimum and started putting these processes in? Okay. And remember, that UV component would also be there, and it's also going in the same direction. So, all right. So, okay. I should talk a little bit about Wacom. So I've just shown you one thing that we're doing with Wacom right now. It's just, we've got some fantastic studies on metal layers, on variability due to PMCs, to dust, to doing a much better job of forcing the stratosphere with volcanic eruptions. We're starting to put in stratospheric sulfates from volcanoes. So all of that goes to looking at the sort of the goal of Wacom, which is to continue to explore the role of downward coupling from the middle atmosphere to the troposphere through chemical and dynamical processes. And my interest is how that might affect seasonal to centennial variability of climate. So we're going to be doing probably the first CMIP6 simulations with Wacom. Because we are going to be running with couple chemistry, we want to do a better job of representing the stratosphere. And those chemical fields that we produce from Wacom will be used to force all of the other CESM models. The ones that are, so it's an expensive model, but we're going to generate all the fields that can then be used to generate, to run the faster models, to do the longer or integrations, or the, say, the large ensemble going forward. So the other interesting thing, I think, is it's some evidence that there's a stratospheric pathway for this variability in the atmosphere, the teleconnections in the atmosphere. And so you really need Wacom, a properly resolved stratosphere, to understand the high latitude response to things like the ENSO and PDO. Now, what would be interesting, and I think there is some modeling responses, that the PDO itself may be influenced by the solar cycle. And that would be a great way of, say, adding some predictability in the PDO by if you could phase lock it. So a small nudging could phase lock the PDO. Okay, so that's this downward coupling. We still need to better specify the solar forcing in the model. The UV, there's still a great uncertainty in the UV variability based on things like new measurements by source. So we want to work more closely with HAO on a better specification of the UV forcing in the model. And also how it responds, and also the X-ray and very short forcing. We have a project called RAISE, Response of the Atmosphere to Impulsive Solar Events, with ACD, ACL, HAO, and CU to look just at that. Okay. So so that's short term, but I think that the new frontier for Wacom is going to be Wacom-X. So Wacom-X, for those that you don't know, is the model that goes, has a model top at 500 kilometers and includes additional electrodynamics. So this is one of the two areas in which I think Wacom-X could make a huge improvement in our current modeling. One is space weather, and in particular looking at the influence of upward propagating waves. So this is a simulation, high-res Wacom simulation, not Wacom-X simulation, run at, I think, 1/4 degree, that Honolulu and HAO, and showing all of these gravity waves coming up from the lower atmosphere. So all these waves will make it into the ionosphere, and there's already observational evidence that waves can affect such things as total electron content in the atmosphere. And we're, in a few years, expecting 2 satellites to be launched, ICON and GOLD. And they will look at this coupling of the lower atmosphere to the thermosphere. So those, we're going to have great opportunities. We need a model to be able to use that data and to understand that data. So Wacom-X, I think, will play a key role in that. And the other one is space climate. And by that, it's, in the long term, obviously the long-term variability of space weather. But and one of the things is that that's going to be now a combination of forcing from above and below. We know that they can continue to have increasing greenhouse gases that means that we're going to have a cooling of the atmosphere. And in the stratosphere, obviously it's warming in the troposphere. In the stratosphere and above, it cools. That means that the whole atmosphere tends to sink. With that sinking, and then on top of that, you could have a grand solar minimum, which means that the atmosphere is not being heated, it won't expand as much. So now the densities in the upper atmosphere are going to go down quite a bit. So there, you go. This is just, I think, a projection. I don't even think that this one has these scenarios built into it. But this is sort of just a figure showing the population of space junk. And there's going to be, depending on this scenario, there could be serious consequences if people don't start thinking about active removal or tethering every piece of space junk that comes off a satellite, and the likelihood that you're going to have a $1 billion satellite be taken out. And that likelihood is going to depend on climate change and on the variability of the sun. So I think long-term simulations, looking at this, trying to span this variation in density would be a great new frontier for Wacom. Okay, so finally I'd like to acknowledge people I've been working on for a lot of the slides here. So Doug Kinnison and Francis Fitt helped me with implementing the medium energy electrons and understanding the chemistry, that chemical response. Mark Clovert at the British Antarctic Survey and Craig Roger at the University of Otago were the ones that actually went in, took the MEPED data and created the ionization or the energy spectra. Pekka Veronen calculated the ionization rate profiles that we put into the model. And I was working with Erkki and Monica on comparing those to GOMOS. And then we have comparisons from MEPAS from Bernd Funke in Granada, and Cora and Lynn here are the ones that we're looking at the HALO data. So with that, I'll end and take questions.
Thank you, Dan. Anybody have questions?
I could ask a really sneaky one.
Yeah.
We think we're beginning to understand the source of these weird offsets. Why energetic things don't peak at the same time as the sunspot number, for example. Mm-hmm. And so I think that's another avenue where we can definitely help. But I'd also be interested to look at the higher frequency modulation of some of these couplings.
Yeah, I have actually no idea why it is that there's this propensity to have these large solar storms on the declining phase. Do you know? Okay.
Oh, we think we know.
We think we know? Yeah.
I mean, these are the outliers that live on the outside of the butterfly diagram. They can only live on the outside of the butterfly diagram for a couple of reasons. So we think it's part of that nasty bandogram picture that these intra-hemispheric, extra-hemispheric interactions drive flux emergence of one system into another, which creates storms. So you can naturally kind of think lead to a phase lag. It's a well-observed effect, solar physics, called the Nevishev gap, and it's a number of years that varies from 1 to n, where the peak in flaring activity doesn't match sunspot prediction.
Right. Yeah.
So I think we're starting to get a bearing on where that comes from. So my question really.
Yeah.
I'm wondering if you have an idea of how accurate the MEPED data are. My understanding of these instruments is that absolute calibration is very tricky, and there's degradation over time and so on that has to be corrected. And that perhaps a factor of 2 difference, is within the realm of the data. So I don't know if you have a sense of that.
Factor of 2 is what I've heard. There's some uncertainty in taking that integral flux and going to a differential flux. And I don't know if there it is. So you can take that integral flux and you can fit it to a power law. And so we did that. And but someone would say, well, it's not a power law. It could be some kind of Maxwellian or some other thing. So there's certainly an uncertainty in that forcing, or just in that differential flux that comes into the model based on your fit even. And this is why I really want to pursue these additional measurements from the new Van Allen probe and this CubeSat, because I think they promise to give us really high resolution here. If we can then calibrate this MEPED data to that, we can then have faith in going back in time for this decadal forcing. But I did talk to, I said, okay, Craig, you know, about what could I reasonably vary this by? And he said, oh, about a factor of 2. So I am thinking of just doing a second simulation or another simulation where we do that. And maybe I'll get better agreement with the MEPAS. I've also just been sent some new data from the Odin satellite, monthly means, climatology, and I start trying to get at the source region, the mesospheric observations of Nox, just to see how well we do at that, and seeing if maybe a factor of 2 might pull us into closer agreement with the observations. So, yeah.
Then, so with the increased Prandtl number and mixing, do you expect more atomic oxygen coming down and give you a better agreement in the MLT region?
Yeah, so you do bring down more atomic oxygen, which you would think would help with the ozone, but the other side of that is it actually brings more water vapor up from lower down. And that HOX that comes from the water vapor through Lyman alpha photolysis will end up destroying some ozone, and it turns out to be a bit of a net zero effect, which is kind of nice. But in that we don't have, you know, if it had messed up the ozone, I would have not been free to change the Prandtl number by a factor of 2. But physically, you can't take it down to much lower than that, I think, on physical arguments.
Dan, in your super recovery discussion, so does your inclusion of EPPs indicate that estimates of the climate impact of super recovery has been overestimated, underestimated? Would that change with the solar cycle?
So if it went into a solar minimum, I think we would be talking about ozone responding even more going forward. So it would be an underestimate. Yeah. I think Cora has a question. Oh, there's a question.
Getting back to this question of the eddy diffusivity, are there any measurements up there of turbulent motions?
Yeah, individual rockets, they do some tracer release type things, but I don't think they're good enough to construct a global model.
You can't estimate directly any kind of eddy diffusion coefficients from the measurements, then?
No, I don't. No.
What is the nature of turbulence up there?
Breaking of the dissipation of waves. As waves go up in the atmosphere, they grow in amplitude and become unstable and dissipate. So small scale waves, gravity waves, that sort of thing.
Yeah, I have a comment and a question. Comment just with the MEPED data, the other problem we have aside from, of course, the power law or whatever kind of spectrum is just understanding how many are actually in the loss cone.
Yes.
As opposed to not precipitating at all. I had a question, though, and I may have misread your slide, but way back when you first showed the results from the model putting the medium energy electrons in, it looked to me, I think, that like in the southern hemisphere, the precipitation in the model was much more poleward than the ACE observation showed. Is that correct? And if so, do you know what's going on there? What might be causing the difference?
You mean the NOY in the upper?
Right.
Yeah, I mean, no, I don't know. That's a climatology, and I don't know how much data they have. That, you know, whether or not that discrepancy between the model is related to a source or perhaps a sampling issue, because I'm just looking at monthly means. We will go back and sample the model on those ACE locations and do that. That would be the best way to do it. Yeah.
Okay. Yeah, it was ACE, so actually maybe they couldn't even sample the pole because they need sample.
Yeah.
Okay.
Yeah.
Thank you.
Is MEE in the other CCMI models, or is there plans to put MEE in the other CCMI models?
No. As far as I know, there's not a single CMIP model that has thermospheric NOx or any CCMI model that has the thermospheric component and the MEE as well. I don't believe either of these processes are in the models. I think Eugene Rosenoff, the so-called model, has done some sensitivity experiments where they've sort of just looked at this, and they show, I think if I show you something. Oh, sorry, a few extra slides here. So this Eugene Rosenoff and Sokol looked at an ensemble of simulations with and without medium energy electrons, and they predict a surface temperature response in Northern Europe, again, where we're seeing that lagged response in SLP. So, but this is sort of more of a sensitivity thing. I mean, the really hard part about it here is coming up with a climatological forcing data set that you can use for decadal predictions to kind of get the long-term climate forcing. Lots of people are doing sensitivity experiments, but no one, really trying to take the observations and do a long-term forcing scenario. Challenge now will be, how do we extrapolate back in time and forward in time for even just putting in this additional NOx, even if it's on a climatological mean, is going to change your base state. So I think even just taking that 10-year average and putting in even just that additional NOx source that is the same as, adds to that source coming from below, is an important part of the puzzle in getting the ozone distribution right. I mean, considering how long we've been studying ozone, I think 7% is it's quite a big difference, really, I think. So.
Okay. Anything more? All right. Let's thank Dan again.